we are, just to make sure we understand, because we've got an upcoming lab here where we are going to, hang on a second. A lab where we are going to actually collect some gas. We're going to collect oxygen gas. We're going to look at, we've talked about the ideal gas law, and we talked about PV equals nRT. We are going to come up with and show you sort of how chemists would have come up with the R constant, how this number came about, how it's measured. So we're going to take a situation in lab where we're going to measure the pressure, volume, and temperature, and the number of moles of a gas in a certain situation, and then we will calculate R from that. Well, in order to do that, what we have to do is collect the gas to start with, and it gets really tricky when you're trying to collect a gas because it's so volatile and it can spread around everywhere. So when we do this, usually your gases are going to be collected in a container that has water in them, okay? Excuse me. And because the volume of a gas is so hard to figure out, because it depends on its container, what typically is done is, I don't know if you've looked at the lab for tomorrow or not, but what typically is done is you have the sealed system, and you have some sort of reaction that evolves the gas that you want, and it will produce it in pure form. Okay, so then that gas will travel through like a hose device or whatever. It'll get collected, and it will feed into some sort of sealed container that has been pressurized so that all the space is occupied, right? So that means if all the space is occupied, if something else wants to come in, something else is going to have to get pushed out of the way, right? So in this particular case, you're going to have a flask that has water in it. You're going to have a big empty space above that water, and you're going to have put a syringe on top and push down, plunged it in, and filled up that empty space with air, basically, is what's going to have happen. So now any gas that is produced from this reaction will come in, and it will have to push out. If it wants to occupy that space, it's going to have to push other things out of the way. Well, in this case, you're going to have a tube that goes to the bottom of this flask that is submersed underneath the water, so that when that new oxygen gas comes in, it's going to push down on the water, right? And it's going to push it up through the straw, glass tube, and kick it out to the side. Okay. Now, what we are assuming here is Archimedes' principle, sort of, in displacement when we talked about density, is that whatever amount of water gets pushed out is equal to the amount of gas that came in to push it out. Okay? So then we can determine the volume of our gas by just collecting a beaker full of water that gets pushed out of the way. And we can measure that in our graduated cylinder, and we can take a volume reading, and if there was 150 milliliters of water spit out, that means 150 milliliters of gas would have formed in this particular reaction. Okay? So we got to get tricky. Temperature is easy. We just, when we're done, we pop the lid, we stick the thermometer in, we take the temperature. Pressure is actually easy as well, because we can just use whatever it is on the outside of us here. There's somebody out there. Realize this: if we have a setup that has a flask and a sealed tube where the reaction is taking place and a hose feeding to this flask, if we have another hose coming off that collects the water that gets pushed out, right? Realize that this little container of water is open to the environment, so atmospheric pressure can push down on that water. We haven't created a system that is entirely sealed up. We have it's a little bit, it can alleviate pressure as it builds, right? That's how it pushes the water out. So what we get is some equilibrium here, and we get a situation that is allowed to balance itself out and exist at whatever the atmospheric pressure is. Okay? As it's pushed up, it'll overcome, and then there'll be a balance, and the total pressure of the system should be atmospheric pressure. So we'll have a pressure, we'll have a temperature, we'll have a volume, and the only thing we need now is the number of moles, and we're going to get that from stoichiometry. We're going to know how much stuff we reacted, do the math, and calculate the number of moles present to start with, how much should have come out. That only leaves us with one variable left, R, and then you can manipulate all of those variables down and solve for R, and you can calculate the value for R. That's the next lab that you're doing. So to do that, though, we have to know how to collect gases, and we have to keep one more thing in mind, and I'll explain that to you. Realize that if we have this container of water and the gas is coming in, that with any sample of any liquid, there's always going to be some molecules that escape the surface and are in gaseous form. Now, we may not see it, but there's always going to be some. And the warmer that liquid is, the more molecules are going to be hovering around its surface that are actually in gaseous form. When we turn it to its boiling point, we've converted all of it. We convert it to entirely in gaseous form. But there's always going to be some that have enough of energy associated with them that they can break free from the surface. Now, that's not going to be very much, but it's going to be some. So what this means is when you're collecting your gas, it means that not only is the new pressure that you are witnessing because of the oxygen that's coming in, but whatever pressure is also in there pushing down on the water is also going to be attributed to some, not very many, but some of the water molecules that have left the surface and become part of this gas mixture that are now pushing back down on the water as well, right? So what we have to do is make sure that the pressure that we use in our calculation does not involve any of those extra gas molecules. It does not involve water in this case, water vapor. We want to make sure that the pressure only involves oxygen in that case. Okay? So how do we do that? Well, this pressure is called vapor pressure, the pressure of the water molecules that hang out. And I'm going to come back to this in a second, but look at this picture. I'm going to turn this down a little bit so we can see it a little bit better. If you look at this picture, can you guys check to see if anybody needs in over there? Just let them in. If you look at this chart, notice that fortunately all this is already prepared for us. This is not something you're going to have to measure. Because we collect gas over water so much, there's already this table that exists that already tells you if atmospheric conditions are normal and this is your temperature of water, it has been proven that this is the amount of pressure that is associated with the free hovering water molecules at those temperatures. Okay, so that's already done for you. You just got to look it up. So notice at 25 degrees Celsius, which is about right here, about room temperature or so, out of atmospheric pressure, 760 right, on average millimeters of mercury, 23.8 of the pressure, 23.8 millimeters of mercury of the total pressure will be in a liquid system of water would be attributed just to the hovering water molecules, not everything else. So it's a very small amount compared to the total, but it's something that we need to subtract out to make our math right. Notice that as we increase with temperature, the vapor pressure of hovering water molecules increases, and that makes sense. The warmer it gets, the more energy they're going to get, the more of them are going to be able to get into vapor form. Now, what that means is, if you collect a gas sample with the total pressure of 758 millimeters of mercury at 25 degrees Celsius, realize that you know that the pressure of water vapor in that case is 23.8 millimeters of mercury, according to this chart. Okay, 23.8 millimeters of mercury. So what that tells you is that if you want to find out the gas, the pressure just that's involved with the gas that you're dealing with, you got to subtract out that 23.8. That's all this is saying. So you would take 758 minus 23.8, consider your sig figs and that kind of thing, and you would get around 734 millimeters of mercury. So you're always going to subtract out a tiny bit due to the hovering water that you're using to collect this gas over. And just use the table to do that. That'll be provided if you ever have to use it. It's not anything you have to memorize. Now, I already mentioned this. This is sort of the same principle. Our setup won't look like this, but the theory is the same. You can have a reaction. If you want to produce hydrogen gas, you know a way to do that. You know enough about chemistry to come up with a way. If I told you I want you to collect some hydrogen gas, that should be a quiz I should be able to give you. And you should be able to think in your head before you freak out, well, how am I going to collect hydrogen gas? Where am I going to get it? Well, what do you know? You know enough about chemical reactions and single displacement reactions, how to make that happen. If you took a piece of zinc, you dropped it in some hydrochloric acid, what's going to happen? Your zinc and your chloride are going to dissolve into solution. We write it as zinc chloride that would actually form, but it's not a solid, right? It would actually be dissolved. You would have floating zinc and chloride ions. But what would happen is that hydrogen gets kicked out and displaced, bonds with itself, right, because it's diatomic, and you get gaseous hydrogen formed. That's why metal sort of dissolves and bubbles whenever you drop it in an acid. We've already talked about all of that. So you set up an apparatus like this, you know that gas rises. It's less dense, right? So one thing to keep in mind is it's going to travel and it's going to always be at the top of something. So as it's allowed to collect and bubbles through and goes through, if the end of it is sealed and it comes up through here, and that gas has traveled from here over to here, it's going to fill up this space. It's not going to stay down here because it's a gas. It's light. It's less dense. So it's going to start to increase in pressure up here as more of it comes in and continue to push out water in this direction as it builds up. But what is important to note is that, notice there's some water molecules up here, because at anytime you do this, some of the water molecules are going to escape the surface, and that's what we have to subtract out, because we want to make sure the pressure we're dealing with is only for these guys and not for all of this together. Okay. Now, just when you thought that, okay, I can handle this, we're going to take ourselves all the way back to chapter 8 now, and we are going to resurrect some stoichiometry. We are going to use chemical equations. How much of it? How much stuff can form? Remember all that stuff? That's coming back now. There's just some twists that we have to put on it when we're dealing with gases. Okay? You'll see that there's a way to use the ideal gas law, which is PV equals nRT, in conjunction with stoichiometry, and that's where we get with gases. Okay, I'm going to come back to this in a minute. I'll mention it now, but in gases, because everything's so spread out, right? One of the things I said that, when you have a 1 mole of a gas, it doesn't matter, because of the space between the molecules, it doesn't matter what the gas is, you'll have the same volume for each of the, well, I'll tell you what, I'll get a slide coming up. I'll save it for then. I'll explain it. But my point is, in stoichiometry, we always use moles, right? We have to get to moles, and then we can use our equations, our chemical equation to say, okay, there's 2 of these for every 3 of these, or whatever. With gases, you can actually use volume as well, because of how spacious the molecules are between them. But we'll come back to that. Don't worry about it. All right. Now, when I say this last bullet, this is very important, so grasp this. Okay? The ideal gas law, well, we can take the parameters of what we're in. If we know the pressure, the temperature, right, and the volume, we can convert that to a mole value for that gas, right? We can come up with how many moles are present for that particular gas if we know those other variables. Once we know moles and we know the chemical equation that we're dealing with, we can then use stoichiometry. Okay? And that's where we're going here. So take a look at this example. It's taking what we know about gases, and it's taking what we go back to what we know about chemical reactions, put them together. So gases and chemical reactions. Here's the equation that we're going to be doing. This is what we're going to be doing in lab. Okay? We're going to do this exact decomposition. What does this mean? Remind me. Okay, heat supplied to the reaction, right? We're going to take potassium chlorate and we're going to decompose it. And when we decompose it, we're going to produce potassium chloride salt. It actually would still be the white crystals that are left behind. Looks like table salt. But also oxygen, pure oxygen. Here's our ratios for the balanced equation. Okay, 2 of these, 2 of these, 3 of these to make everything work out. All right, we are also going to, in lab, just so you know, there's going to be another chemical involved that's not going to participate in the reaction. It's going to act sort of like a blanket to sort of smother some stuff and to keep stuff from spattering all around. It's going to just slow things down for us. Otherwise, if you just stuck this under a flame, it decomposes very, very quickly. It would bubble very violently, build up a lot of pressure very quick, and stuff starts popping and breaking and blowing. Okay? So instead, we're going to use MnO2, manganese. It's called manganese dioxide, but the proper, of course, according to the way we name things, manganese 4 oxide. Okay? And it's going to be like a black powder, and you'll mix it in with your potassium chlorate, and it'll just slow some things down for us. Okay? It's not going to affect our chemical reaction. This is still the only thing that's happening chemically. All right, so we're going to evolve oxygen, pure oxygen. Now, there's no way of knowing anywhere along these lines just how much oxygen got collected, right, in terms of moles. There's no way that you can't grab all of this and pull it out and stick it on a scale. It's way too hard to do. Okay? There's nowhere along the way that we can actually physically take a measurement of the amount of moles of oxygen present. But we can still know how many moles of oxygen were present. If we know, how much of this we started with, right? If I told you to weigh out a sample of this, and you weighed it out in grams, you could convert that to what? Moles. You add up to get the molar mass, right? And you convert your grams to moles. Once you know how many moles of this you have, look at the stoichiometric ratios. You can figure out how many moles of this would form, right? So what you would do then is predict according to what you started with. You assume that all of this reacted because it stopped bubbling, okay? And then everything that you collected, you could mathematically infer how much of it formed without ever actually measuring it. Okay, do you see how that works? That would be N, right, the number of moles. All right, well, here's my question for you, though, and that's what you're going to do in lab. That's how you're going to find N for oxygen. Your P is going to be atmospheric pressure. Your volume is going to be the amount of water you spit out. Your T is going to be when you stick the thermometer in, whatever the temperature is. Then you're going to arrange those variables, and you're going to solve for R and see if you can get 0.0821. That's what the purpose of the lab is. But in this particular case, how many liters of oxygen gas form? If I have 294 grams of this stuff, it completely reacts, it decomposes, and as I was monitoring this system, the external the pressure of everything going on was 755 millimeters of mercury, somewhat close to atmospheric pressure, and the temperature was pretty close to room temperature. Room temperature is 298 K. Here's 308 K. Okay, so here's my temperature. Here's my pressure. I want to know if I have this temperature and this pressure and I'm starting with this much of this solid, how many liters of oxygen will form? Can I figure this out? Well, obviously, or I wouldn't have put it up here, right? Now, notice that we go back to what I said a minute ago. Part of chemistry and part of succeeding in chemistry is not just how good you are at math. You could be the best math person in the world, it doesn't matter. You could have got an A in math, it doesn't mean you're going to get an A in chemistry. Because the difference is, you're not just doing math, you are taking math and specifically using it to solve a problem. There's two parts of a chemistry problem. Number one, figuring out where you are versus where you need to go and coming up with a way to get there. Once you figure that out, you're halfway done. The other half is doing the math that gets you from point A to point B to point C to point D. So before you even start, what so many people make a mistake in doing is they slap some numbers down, they try to label it, and they try to multiply things together, and they get lost along the way. We come up with these solution maps. They're called maps for a reason. It takes you from where you're starting to where you're going. You have to think about how you're going to get there. Make a plan in your head before you ever start. Otherwise, you're just going to have this string of numbers that don't make any sense, and you're going to have no meaning in it. So, think about what you have. You have a mass measurement for this. You have a chemical equation that's probably obviously going to be useful, or I wouldn't have given it to you. The only way that you can use a chemical equation is if you have moles, right? So what that probably means is, and everything that we've been talking about this chapter, you've not seen grams written anywhere. You've seen P, V, R, T, N for moles, never grams. So two things should pop out. Number one, this is going to have to be converted to something, okay? Because I'm not going to use it for grams. Number two, what is it going to be converted to? Well, I see that I've got a chemical equation, and I am starting with reactants, considering something in products. That means I'm moving from this side to this side, and I cannot do that unless I perform reaction stoichiometry, unless I look at my mole ratios and see if I have 2 of these, 3 of those conform, kind of thing. Okay, that's the only way I'm going to be able to move, and I can only move through the value of moles, the unit of moles. So it makes sense that I'm probably going to have to convert that to moles, and that's going to be part of my path somewhere that I'm going to use. Okay, so if I take this in moles, right, you tell me. I've sort of already been through this, but let's reiterate. You tell me. If I convert that to moles, I know moles of potassium chlorate, right? What am I trying to solve for? I'm trying to solve for liters of oxygen, right? Okay, now everything about this chapter has been one of two things. Either you've got changing conditions, P1V1 equals P2V2, or you've got a static condition that involves the equation PV equals nRT. There's a divide for the chapter, right? Which of those cases applies here? PV equals nRT, right? I don't have changing conditions. I don't see two different pressures, two different temperatures, anything like that. I see one of each thing that I see here. So I'm going to be using the PV equals nRT equation. That is going to be involved in this somehow. So take mental note. All right, so how am I going to put all this together? You got to think about what you're doing here. Think about the setup too. I have a weight or a mass of potassium chlorate, right? Ultimately, I want to get liters of oxygen gas. What's the symbol in our equations for liters that we're looking for? Of PV, R, and T, and N, what am I looking for? The V, right? That's volume. So I see liters and I think volume. I'm going to be using PV equals nRT, so that must mean that I am going to solve for volume using PV equals nRT at some point in this equation. So what that means is I'm starting to plan out my map here. Where I'm wanting to get is volume. Okay? I'm starting over here at grams. I need volume. I know that to get volume, I'm going to have to use PV equals nRT. Now, in order to use that equation, I'm going to need to know what these variables are. Right? I'm going to need to know P. I'm going to need to know N. I'm going to need to know R and T. Well, fortunately, R is always constant. It's given. Never have to worry about that. I see that I already know T, right? I see that I know P. This has already been given. Okay? It didn't say anything about the water in all this case right here, so don't worry about that. I'm telling you, I've already got that measurement for you. Here's P. Here's T. I'm solving for V. I know R. There's one thing I'm missing, and that is N. That's where reaction stoichiometry comes in. Okay? I have to calculate N from what I know here. So now I look at this, and I realize, okay, I know how many moles. I can convert that to moles. I know how many moles of this I have. Okay? If I know how many moles of this I have, I do one math step, noting that there's a 3-to-2 ratio here. I can come up with a number of moles of this. And once I do that, I know P, I know N, I know R, I know T, I solve for V, and I'm done. Okay? The only other thing to keep in mind as you go through this is a pretty, this encompasses a lot. This encompasses everything that we've talked about. Knowing chemical equations, knowing how to balance chemical equations, knowing reaction stoichiometry, knowing the gas laws, all of it together. So it looks simple, but it's a pretty involved problem, right? One thing to keep in mind is that if we're going to use R, that 0.0821, remember what units have to be present so that that number applies. Liters, ATMs, moles, and Kelvin. We have Kelvin. It's already converted. No need to convert. Problem here, right? We're going to have to make sure, and people do this all the time, so realize that you have the pressure, but you don't have it in the proper unit that you need to use for R. So you have to convert that to ATM. We're going to have calculated moles, so that's okay. And we're solving for liters, so we'll get that. All right, so it's a lot of stuff. Let's write down what we know here. This is whenever we convert. I told you, you'll come into these things whenever you need to write them down, but I write all mine up front here. We know that if I'm going to have to convert my gram value to moles, so I'm going to need the molar mass. So if I add this up, I'm going to know that 1 mole of potassium chlorate weighs that much. There's the molar mass. My reaction stoichiometry is going to involve this ratio. 2 of these for every 3 of these, okay, present. We decide that we're going to use PV equals nRT in here somewhere. These are all things I'm just jotting down so that I can use them when necessary. So this is where we make our map. And this is an easy place to get lost, so let's figure out where we're going. We've already walked ourselves through it. Sketch it out if you have to. You're at grams. Ignore the numbers for now. You're at grams. In theory, this equation is useless to you in grams. Pretty much guaranteed in this chapter especially. You see grams, you're going to need to convert that to moles. So your first step should be converting that to moles. All right, now that we're at moles, what's the next logical step? Well, I'm trying to get to way over here on the other side. Should be liters or volume of oxygen, right? How am I going to get there? Well, I've got to get to oxygen. I've got to get to oxygen before I can even think about what about oxygen I want to know. So how do I get to oxygen from potassium chlorate? Right there it tells me how to get there. Okay? I know how many moles of this I have. I'm trying to get to oxygen before I can even worry about liters. So I'm at moles of potassium chlorate. I know there's 2 of those, for every 3 of those, for example. I can go from moles of potassium chlorate to moles of oxygen, right? Now, once I'm at moles of oxygen, so now I'm dealing with oxygen. And I can look at the conditions specific to oxygen and realize if I want to get liters now, I can, because I've got P. I've got V. I've got P. I don't have V, but I do have N, R, and T, right? So I can plug in the numbers that I need. I'm there. So that's what I'm going to use. And then I can get to VO2, which would be in liters. That's what we have to have for R. What just so happens that's also what this is asking for. If I ask for something else at the end, you would take those liters and convert it into another volume. Okay. All right, so here's the math. Now you've got that figured out. Make sure this makes sense before you ever start plugging in numbers. Then we can figure out, okay, I say I go from here to here. How do I do that? Well, to get from grams of potassium chlorate to moles of potassium chlorate, I'm going to have 1 mole up here, and however much 1 mole of it would weigh down here. It's molar mass. I've got to know which ways so I can cancel things out. I've canceled it out. Now my answer is left in moles of potassium chlorate. I want to go from moles of potassium chlorate to moles of oxygen. How do I do that? Coefficients, right? I know that for every 3 mole of oxygen produced, 2 moles of potassium chlorate had to have been used to do that. So I put them to where they're going to cancel out. I'm at moles of oxygen. Now, I'm going to use PV equals nRT, plug in what I know. P's up here. Remember, I'm going to have to convert that to ATM, though, right? V is what I'm solving for. N, I just calculated right here in this step. R, I already know. T is already given as well. So we're in good shape. So there's my mole of oxygen. That was this part right here, getting up to this yellow square. Okay, moving up to there to get to moles of oxygen. Oops, sorry. That's this part. On 3.60 moles of oxygen. Now, to use my PV equals nRT, we had to convert our pressure to ATM. Here's that conversion. Remember, 1 ATM is 760 millimeters of mercury. I give you a list of all of those. We do our conversion. Now remember, with sig figs, as we do this, you want to make sure you don't round off prematurely, because we have more math to do. This is all one giant problem that we could string together in one step, sort of. Okay? So what that means is, if you're converting this to ATM, don't round off yet. We'll only round at the very end, or whenever we need to. Just make a mark to where you would round off, if you needed to, and keep that in mind. Okay, so we plug it in. We are solving now for V, so we rearrange our equation. V is equal to that, nRT, over P. We plug in our numbers. Here's N, here's R, here's T, here's P, and we get an answer of 90.7 liters of oxygen. Okay? Pretty involved problem, but you can see where the discoveries of all these guys that we've been talking about made it possible to deduce this stuff about our chemical world. Taking these situations, especially dealing with gases that are very hard to deal with, and come up with answers that we need to know. Okay. Questions about this problem? Don't even know what to ask, huh? You'll have to do this. I mean, it's a pretty involved problem that shows me that you know all the stuff that we've been talking about. Okay, now I want you to note something here. If I asked you this question, and I said, calculate the volume occupied by 1 mole of an ideal gas at STP. What does STP mean? Standard temperature and pressure, which is, standard temperature is what? 273 Kelvin, or 0 degrees Celsius. Standard pressure? 1 ATM. Okay? So that means I gave you a bunch of data just by that abbreviation. Make sure you can realize that. All right. I want to know the volume. If you're at STP and you have 1 mole of a gas, doesn't matter what gas it is, because they're all going to be the same. Tell me what the volume is. And you set it up. Here's your P, solving for V. Here's N, R, and T under the conditions. Notice you get 22.4 liters. This is a very important number. Okay. What this says is that if you have 1 mole of a gas, no matter what the gas is, at STP, if you have a gas and it's at 273 K and it is at 1 atm, every gas under those conditions, if you have 1 mole of it, will occupy 22.4 liters. This is called the molar volume. It's another conversion factor is what it is. It basically says that 1 mole, now, I realize this, I should have this like flashing lights with little like carnival sign around it or something. This is only at STP. Let it out, man. Don't hold that in. Only at STP does this apply. No other conditions. At STP, 1 mole of any gas is equivalent to 22.4 liters. That's how much it will occupy. Now, I say this, you can get away with never having to apply this. Okay, but I'm going to show you another way to solve a problem. If you understand sort of what we've been talking about here, you can see this as a shortcut. If you've been lost, everything we've been talking about, you're going to see this definitely not as a shortcut. Okay, but I'll show you it nonetheless. All right, but just to illustrate my point, at the beginning I said I was going to come back to this, so this is where I'm coming back to. Here's helium, here's xenon. Notice that xenon is a much larger atom than helium is, right? However, at 22.4 liters, let's say this box held 22.4 liters, and this box held 22.4 liters. I want you to notice that it doesn't matter how big this atom continues to get because it doesn't affect the amount of space that it takes up. And the reason that it doesn't affect the amount of space it takes up is because look at all the huge amount of empty space that's between all of these atoms. I could make this bigger and bigger and still have plenty of space between all of the atoms. That's why I say that at 1 mole at STP, it doesn't matter what gas you have, they all occupy the same amount of volume. Okay? The only way that becomes not true is like in the cases with liquids and solids, where these things are so much closer together, the size difference takes up more space and pushes other things out of the way. And then you don't have that constant. You don't have a constant volume under conditions and things like that. With gases, you do. I can take something really tiny or really big. It doesn't matter because I still have tons of space in between them all. So regardless of how big they are, look, the mass of 1 mole, if I had 1 mole of helium atoms floating around in here, it's only going to weigh 4 grams. If I have 1 mole of xenon, it's going to weigh 131.3 grams. Huge difference, right? It's going to weigh a lot more. But the volume is still going to be the same because even though it weighs more, there's still a ton of space between them all, and the size that contributes to the mass doesn't matter because they still got plenty of room to spread out. So that's why that 22.4 liters thing remains true. All right. So let's see if we can answer this question. How many grams of water will form when 1.24 liters of hydrogen gas at STP completely reacts with oxygen? So you're combusting hydrogen here. Notice, though, that as you read and listen to the news and hear more about like hydrogen as a fuel, things like that, one of the big attractions of using hydrogen as a fuel source is it's the cleanest possible reaction that we can run because the only product formed is pure water. Okay? And realize that whenever water forms, one of the things that I've already shown you, or showed you, or whatever the past tense I should have chosen there, is I can take this water, I can run an electrical current through it, and separate it back out into hydrogen and oxygen. Remember that? You remember that? I talked about that before. If you take a water and you run it, and you hook up a wire to a battery and let it pass through the water. Remember, I had a picture that I had test tubes on there that it would take the water and split it electrically, and that electricity would split the water into hydrogen and oxygen. You can do that. Well, if you could create a situation where you could combust hydrogen and in that somehow if you could like play with the pressures and build enough pressure that the movement and the making of this gas turned like, I don't know, say like some sort of little magnetic motor or something that would generate electricity, then you could take all the water, the waste that forms from this, use that electricity from the formation that you've made, split that again, and recycle this and create this perpetual loop to I don't know, maybe run an engine, so to speak. in theory, that's not completely possible. You're going to lose some stuff along the way, but you see how good of a source it could be. The problem is, of course, is this is highly combustible, right? This is, hydrogen and oxygen is rocket kind of stuff. Put this in our automobile creates a little bit more of an issue. Hydrogen fuel cells are a little bit different. They're a little bit smaller and that kind of thing. But anyways, we see that this becomes very important in outer space on the space shuttle. Recycling oxygen from waste, stuff like that. Supply electrical current, collect some solar energy, use that to generate some electricity, take whether it's bodily waste, water vapor that you breathe out, all that kind of stuff. You can actually electrolyze it, bring it back around, and produce more oxygen out of the water that's actually produced from our waste. So, interesting. Anyways, you have 1.24 liters. Crazy. People think there's some crazy stuff out there. We just don't really think about how it works, but someone has to. Anyone ever think about that, though? Do you ever stop and think about the fact when you're sitting out at night, you look up at the moon, especially on those days when it's really close, times of year when it's really close, you can see it perfectly clearly. Someone stood there. Someone was able to walk across there, and it's amazing. It's amazing. Anyways, 1.24 liters of hydrogen at STP, so 273K, 1 ATM. All right, what do we have to use if we're going to find out how many grams of water forms? What are we first going to have to find out about water? How many what form? Moles. That's right. All right, so in order to find out how many moles of water form, whenever the only thing we know is something about our reactants, we're going to have to use stoichiometry, right, to answer that question. All right, so that means I'm going to have to go from, the only data I know involves hydrogen, right? I'm going to have to take what I know about hydrogen, somehow get it into moles, so that I can move from hydrogen over to water. And then once I'm at moles of water, I can answer my question about grams of water. Okay? So how can I take what I know about 1.24 liters of hydrogen and convert that into a mole value? Any thoughts? That's right, because I'm at STP, right? Now, I want to point something out. We can do this the exact same way that we just did on the other problem, right? If you know PV equals nRT, then realize you know P, you know V, you don't know N, but you know R and T. You know everything because I tell you STP, that implies two of those variables, right? So you can use PV equals nRT and solve for N in that equation, and you get the same result. The reason that it's a little bit of a shortcut is because at STP, we've got some work that we cut out. We don't have to worry about doing all that, what I just said, because we already know that 1 mole is equivalent to 22.4 liters without having to do any math. Okay? Now, if that is not the way that you prefer because it's too much to remember or it confuses you, realize it doesn't matter. PV equals nRT will also work. Because it is PV equals nRT, it's just that we've already substituted in the 1 ATM and the 273K. We've already done some calculations to get to that 22.4. Okay? So either way, it's going to work. The bottom line is you got to get to moles to make this work. All right, so write down what we know. I'm going to need to convert from moles to grams of water, so here's the molar mass. Here's my reaction stoichiometry. It's a 2-to-2 ratio. I know this. Should I need it? 1 mole of hydrogen is equivalent to 22.4 liters since we're at STP. So I'm going to make my map. I'm at liters of hydrogen. I'm going to need to go from liters to where? To moles of hydrogen. Good. From moles of hydrogen to moles of water. That takes me there. Once I'm at moles of water, I can go to grams of water. Right? Now I've got my map. How did I get from each point to the next one? Well, from liters to moles, I chose in this case to utilize this ratio. Please do not do this unless you're at STP. It will not work. Okay? Only at STP. At STP, I know this is true. So that takes me to moles of hydrogen. How do I go from moles of hydrogen to moles of water? My equation, right? It's a 2-to-2 ratio. So there it is. Now I'm at moles of water. How do I go from moles of water to grams of water? I use the molar mass of water, right? So there we go. I plug in my numbers. There's my answer, a little under 1 gram. If I use 1.24 liters and I operate at STP and I combust it with all the oxygen that I need, I can form about 1 gram of water whenever I'm done. Okay, 0.988 grams. Questions? Suggest you stay on top of this stuff. No questions at all? Good, you know everything. You guys are unbelievable. Okay. That's all I've got.